also these current spikes produce some overshoot on the voltage. And normally you would expect some 2 or 3 times the normal power supply voltage, DC voltage, to be on the motor winding.
So it's not something you have to, for example, buy extra for the motor, it would be already included?
I think you have to specify that you are using a drive. Because it's different, but when you use a smooth DC voltage or a spiky square wave, it makes a lot of difference for the winding of the motor.
Okay.
In terms of isolation, eddy currents, maybe.
Stress.
Stress.
Right? So it will give you faults.
Yes.
It will destroy the isolation at some point, and then the motor stops.
The practice is
this high stress on this motor, you will destroy the windings, and then you will have a short circuit, and you can take another one.
so well, it should not be rated to 12 volts, but if you use a converter, it should be rated to at least 50, 100 volts to be safe.
And also the VDG.
Yes, of course, yeah.
Really sensitive to that.
So in industrial motors like this, it's what we call isolation class. It should be F or higher. So when you don't use a motor that is suitable for a variable speed drive, then you will see in a few months' time that your insulation becomes brittle and you get a short circuit. And bearings will go kaput. Bearing currents. It's not unimportant for cars, I think. When you've got the bearing currents on the drive, that may go through your lubrification. So you get pitting on the bearing.
No filter will go through your bearing. The common water current will go through the bearing.
Sorry, what we have this one. So the current here, I've got some 6 amps flowing like this. Yeah, but it actually has to go through your oil film. So you rather have maybe some shocks on the output here to reduce the current as well. So reduce the VVDT. These are the 2 master sinks, so the windings and bearings associated with the drive. So we have this one. So here's some mechanical things. That's good.
Out of the wires, there's some shielded on the mains. That's obviously on purpose, but I'm not understanding why.
The mains.
No, it says the mains cable doesn't have shielding. It isn't. The clamp isn't onto the shielding.
Ah, sorry, that one. Yeah. Well, actually, because this is supposed to be a filter inside, so actually the power supply side should be clean, but you need a filter.
Okay.
Otherwise, your filter power supply will go through your drive.
Okay.
If you have a shield, you should connect it somewhere, but it's not possible to connect it.
Yeah. You see some instructions sometimes that they show a shielded cable, but they don't tell what's going to happen here on the other end.
Yeah.
Yeah. Okay. So, okay, this is a way. This is the gland. You've seen the pictures in the last slide. You could also do a connector with a metal cap on it, which connects then the shield to the metal plate here. Instead of a gland, you could use a connector instead. The idea is the same. You keep a continuous conduction between the shield here and this metal plate you want to use for shielding. Okay, get to the next thing. Current boundary. We called it in this last picture, but this is then the basic principle. This is the wire. Most simple experiment I have. Don't try this at home. It's on the ground of the main somewhere there. Could then be a laser start if you take the wrong wire. Yeah. his oscilloscope, his variable speed drive. We go to the medium wave. Look for a quiet spot. It's difficult nowadays in an industrial environment or railway. Okay, this is my wire. I connected between two grounds, and I use my radio. You can hear there's currents. There's a magnetic field coupling to the antenna inside. So this is current that's there. As soon as you connect this wire on two grounds, you get this current. It's coming out of the building, the fields that are here. Currents going from the mains ground to that ground. So there's noise always there. Nothing you can do about it. It's not your responsibility, but it's there. Okay, now you can measure it with the radio. This is the practical situation where you say, okay, we have equipment here connected to one ground here, other equipment connected to another ground, let's say the mains cord, and the car would be the power cord, and then there's a data connection between this and this. This could be a control unit, computer, and that could be the motor, and this would be a speed drive, whatever. And there's a connection, and then you get current over that. If it's a noisy cable with noisy current, it could create this current in the outside world. If it's a sensitive cable, you would pick up this noise, could be picked up and brought into this unit. Now what we want to do is protect the units against this outside world current. I mean, the cable could be able to handle it, but the units you want to spare. So you have to think of a way to protect these units. And what you do, you create an inner loop. So this is a long wire. I create an inner loop and then make a short circuit here. So again, this is a short circuit activity. Connecting a shield on both sides of the cable is also a short circuit activity. Works perfectly for high frequencies. Not so good for low frequencies. For low frequencies you would probably cut this wire and then it will be open. But that only works for low frequencies. For high frequencies you have capacitance and it's still full. So for high frequencies sometimes the measures are a little different than for low frequencies. Sometimes there's a hybrid possibility. We don't do that this afternoon. You can use both. Okay, short circuit is high frequency. Solution, I have these two lugs here. To do that, so we switch it on again. This is the noise. I short circuit, and the noise is still in this wire. I mean, there's nothing changed here, so if you put this here, see, it's still there. The current is still there. But due to this short circuit, it does not flow to the radio, because this is a detour. And the current always takes the shortest path with the least amount of energy. So if you make an inner loop and the current is in the other one, then it won't go into this. The only thing is, well, we have induction, you know. This is a loop and this is a loop. Now I have two loops. And there will be crosstalk, magnetic crosstalk. So what you do is you keep these together, you keep these together to make it good and keep it good. And this is important that it's there. But it doesn't need to be a hard short circuit. You could use a capacitor. I have a special prepared capacitor here on a plastic block. Somebody's making a telephone call. Another sort of noise.
That was one of your questions, not me.
You can also treat it this way. Okay, this is a capacitive way. See? It's only the high frequencies you need to do. So if you have a high voltage on this one, you cannot connect it, short circuit it, because you have a problem there. But if you have a capacitor, you could do it like that, so that you take the high frequencies off and leave the low frequencies go. That's what actually happens in a filter. A filter has a neutral and a line and a ground. And the idea is to connect the line and the neutral both with the capacitor to the ground. Not hard, but with the capacitor. So it's not short circuit, but the high frequencies can go. The 50 Hertz can go through, but the high frequency will be stopped. And that's the idea. And this is called the current boundary, which is a very important thing